Alright YouTube, so now we are going to take a look at acid chloride reactivity, and this is part 1. So there was a previous lecture to this lecture which was the basically the carboxylic acid derivatives, and we were looking at all of the different compounds that we could make from a carboxylic acid, and this included things like acid chlorides, anhydrides, esters, and amides. So if you haven't checked out that video, I would strongly encourage you to look at that lesson before continuing on here. And now we're going to take a look at acid chloride reactivity, and this is part 1. We will definitely be breaking some of these derivatives up into 2 parts given the number of reactions that they can undergo. So as we get started here with acid chloride reactivity, remember an acid chloride is going to be the general formula an R group, C double bond O, and then we have a Cl here. Now I did just want to mention, sometimes students will ask about what about acid bromides or acid iodides, because you could technically have other halogens there. And yes, that's true, you could have other halogens, but as you increase the size of the halogen, meaning you go from chlorine to bromine to iodine, the leaving group gets better and better. And it turns out that the halides are much more reactive as leaving groups when they're attached to carbonyls than when they're attached to just regular alkyl groups. And so while we may have, in theory, acid bromides and acid iodides, you tend not to see them as often simply because they're so excessively reactive that acid chlorides suits us well enough as far as any synthetic purposes and what we'd be looking to accomplish. Now, how do we create, because all of these come from a carboxylic acid, how do we create a carboxylic acid going into an acid chloride? So what we would do is we would start with a carboxylic acid, and when we have that carboxylic acid, the reagent that we're going to use in order to accomplish this is SOCl2. And when we use SOCl2, we will turn the carboxylic acid into the acid chloride, a much more reactive derivative. That's why we call it a carboxylic acid derivative. Notice that we still have the carbonyl. We have a partially negative type of compound here, so very similar. That's why we would call it a derivative. Now, how this actually works, when you take a look at the SOCl2, this would be the general structure for SOCl2, and it's the oxygen on the carboxylic acid that can come in, and when it does, it will attack the sulfur. Right? Now, as this occurs, we can form an intermediate here, and this intermediate would look something like this. So I still have the carboxyl group there, right? The oxygen, here's the hydrogen. This would now have a plus charge because it sent out some electrons to the sulfur. The sulfur would have this general form at the moment, and we have a chlorine and a chlorine here. Now, one of the chlorines is going to leave because chlorine is a good leaving group, and as that happens, the set of electrons here can come back down. As this chlorine dissociates, this or another base that you might have in solution is going to come and pick up the hydrogen here. So I'm just going to represent this as base, okay? But a base of some sort is going to pick up that hydrogen in order to create the oxygen in its regular state without the formal charge. So what this leads to is you've got the original portionality of the carboxylic acid. Now this is attached to SOCl, and this is going to turn out to be a decent leaving group because I can generate sulfur dioxide and another chlorine out of this. So what will happen is the chlorine right here that I just liberated is going to come back in as a decent nucleophile. So this chlorine here, okay, chlorine tends to be a weak base, but it's a good nucleophile. This chlorine here is going to come into the carbonyl here. That is going to force this carbonyl bond up because the carbon can only have 4 bonds, right? The oxygen will need to take that extra set of pi electrons in the meantime. And so what this is going to lead to, all right, I'm going to give myself a little bit more space here. I'm going to scroll down. What this is going to end up leading to is I have R, C, O minus up here. Okay, and I've got the chlorine down here, so I've got this sort of tetrahedral intermediate, and then the oxygen. Okay, now remember I said that we can create sulfur dioxide and chlorine. This can very easily come apart into those 2 stable molecules. So I should say chloride, okay, is going to leave, and then this oxygen will go ahead and give these electrons over to the sulfur. So this is going to be SO2 and Cl as the side products, and then as that's occurring, this would come back down. And so the final result here, okay, would be that I get the acid chloride, and then I also have as side products SO2 and Cl minus. And there you go, you now have your acid chloride, and you can utilize this for other reactions. So let's take a look at some of those other reactions, the ones that we can utilize given the acid chloride. So remember, the acid chloride is the most reactive of all the carboxylic acid derivatives. So we're really going to see the largest number of potential reactions in the acid chloride series, then the anhydride, then the ester, and then by the time we get to the amide, we're very limited in the number of reactions we can do, because that general chart that we went over in the previous lecture shows the reactivity where it says, you know, the acid chloride's at the top, then the anhydride, then the ester, and that's really based on the leaving group. So I'm going to give an example here. One of the first things we can do is all of the derivatives have the ability to go back into carboxylic acids. So all I would need in order to do this is to run this in the presence of H2O, and you usually need a base of some sort. A very popular base to pick out in this case is pyridine. You'll see many of these reactions being run in pyridine. It's affordable, it's a cheap, decent base. Hydroxide is another popular choice for a lot of the derivative reactions. So what's going to happen here? The water is going to come in, all right, it's going to act as a nucleophile, and when I do this, I will end up with the, again, tetrahedral intermediate. We're going to see this as a very common theme as I go along, right? So here we go, and now I just got water to come in here. Remember, it comes with the positive charge. This is not OH yet. So the chlorine is going to leave in this case, and when that happens, right, this would come back down. Now some people might show this occurring in the same step where the proton removal is going to occur. I don't mind showing it in a separate step here. The chlorine's gone, so now I'm dealing with basically a protonated carboxylic acid, and in order to polish this off, the pyridine, the base, okay, is going to come in and abstract the remaining proton. So we'll get rid of that, right? The electrons can go there, and then we arrive at the respective carboxylic acid. So this is really the opposite of what we just accomplished, right? We took a carboxylic acid, we turned it into an acid chloride. So now we're saying we can take an acid chloride and turn it back into a carboxylic acid without a problem. So one of the other types of reactions we can do is going down the list. After the acid chloride, we find the anhydride. So the anhydride can be created by taking another type of carboxylic acid and utilizing it as the general nucleophile. So I have the acid chloride here. What I would need in this case, and again, I'm going to be looking for some sort of base here that goes along with this, and we'll talk about why here in a second. I would create a reaction with another equivalence of some carboxylic acid. These can be the same. Sometimes it turns out that it's better if they're the same exact compound. However, when you're working with this, you will end up with an anhydride. So what's going to occur here is that the carboxylic acid in the presence of the base, okay, is going to be deprotonated. And so what I'm going to create here is a resonance stabilized base, right? Conjugate. So with this, I can then send this group in order to displace the chlorine. So, right, I get the regular attack. I now have R, C double bond O. I'm going to have an O, and that attacked a C. This O is O minus at the moment that had the chlorine on it, right? There's another R here, and this is a Cl. So take a look here. I'll change the colors just so people follow along. All right, this portionality right here came from the acid chloride, and then that's in the red. The one in the blue came from the carboxylic acid. So we're really fusing these two parts together in the reaction that I just showed you here. So once we are set with that, all right, let me switch back to my black ink. Once we get to this intermediate, we can get the chlorine to leave, we can get the group right here, this O minus, to come back down, and we end up with the anhydride. So remember, an anhydride has two carbonyl groups with an oxygen in between them. And this would be second on the reactivity list. So acid chlorides can create anhydrides because they're less reactive, but anhydrides are not going to be able to directly create acid chlorides. As you move down the list, you have to go back up to a carboxylic acid in order to create any of these other additional ones. All right, so now that we've taken a look at that one, I'm going to go ahead and take a look at the ester formation. We can keep our general acid chloride there. All right, so now if I would like to form an ester, I need some sort of an alcohol of choice, and then I will again use a base. So notice most of these are going to require a base of some sort. So I'm sort of switching back and forth between pyridine and hydroxide, which are two common examples. So in this case, I'm going to have the alcohol come in and attack the carbonyl. Right? We're going to do our normal tetrahedral intermediate. I get O minus, and then I would have HR, right? And that would be a positive oxygen right there. And then I have the Cl here. So in the usual fashion, the Cl is removed, right? This can come back down. And when I do this, right, I've got the O and I've got RH here. So at this point, I can now use the pyridine to come in and take the hydrogen away from what was originally the alcohol, and this will create the ester functionality that I need. So moving up here, I now have OR. Okay? And then the last one we're going to take a look at in this lecture is how we can use acid chlorides to create amides. And then there's a whole nother set of reactions we're going to take a look at in the next lecture, which will be part 2. So we will bring up one more time our acid chloride here. Now the acid chloride this time is going to be exposed to some sort of an amine group in order to create the amide. So sometimes, I'll just put a note over here, sometimes this reaction is run with 2 equivalents of amine. All right? Now I'm showing NH3, just general ammonia in this example. There's no reason that this can't be, NH2, CH3. That's a perfectly fine amine. There's no reason this couldn't be double, so 2 CH3s and then just NH. All right, all of those would be perfectly acceptable examples when you're working with amines. It doesn't just mean ammonia, even though that's the one I'm going to be showing in this example. So I want people to keep that in mind, that you can certainly use primary and secondary amines when you're getting ready to start attempting to do this, okay? Now, a lot of times 2 equivalents is used because amines will act as decent bases. So one equivalence of this is going to be used for the actual reaction, the addition. And then the other equivalence is going to be used as the base in order to remove the unneeded hydrogen. Now, sometimes you will find that instructors only give you one equivalence and then there's another base present. And that is also true in the lab. If you have an amine that you're going to add that is very expensive and costly, you're not going to double up with a second one as a base, because that's a very expensive technique in order to, let's say I have an amine, right? And the amine is $100 per gram. It would be very wasteful for me to turn around and take that precious amount of amine that I have, the 1 gram, and say, oh, I'll just add double the amount than what I really need because some of it needs to act as a base. No, you get, pyridine or sodium hydroxide or something cheaper at that point. So I just want to point that out, that this can be run with 1 equivalence of amine and then an equivalence of a cheaper base. All right, so we're going to do it with 2 equivalents of amine. So we're going to say that we have 2 NH3, and that should be all that we need here. So the nitrogen, I'm going to take one of them, and this should be getting very repetitive by now. You should have a good understanding of how this is working, right? So tetrahedral intermediate, I'm going to have the NH3. Remember to never toss out protons until you've shown what's happened to them. This is a carbocation here. I'm sorry, just a plus, not a carbocation on the nitrogen. And then we've got the chlorine, right? The chlorine's going to leave. This is going to come back down. And then the amide is going to be a protonated amide. Sorry if you guys hear any background noise. The lawnmowers are going outside like crazy. All right, so this is a protonated amide, and then the other amine group is going to come in to grab this, and then I end up with the amide, right? NH2. So there you go. That's our first set of reactions. We learned how to turn a carboxylic acid into an acid chloride. We then learned the reverse of that, how to take an acid chloride back to a carboxylic acid. And then we learned how to turn the acid chloride into the other derivatives, including anhydrides, esters, and amides. So you've got all of those potential reactions that you can work with now. Hopefully everybody found this to be a useful lecture portionality for acid chloride reactivity. Again, I will be releasing a part 2 that'll start talking about reduction and Grignard reagents and a couple other techniques like that, where your acid chloride is going to undergo a double reaction, and we'll show you exactly what that means next time. So please remember to like the video if you found it helpful. I'm happy to take any comments, and if you enjoy the videos and you're going through a course right now, please subscribe to the channel. It helps to support making content like this. And I'm also going to be releasing a video soon. I have courses that I'm rapidly putting out on the platform Udemy. So I'm trying to promote that. That's a great way that you can support the channel. The courses are very affordable. They're less than what would normally be about an hour of tutoring. It will have all the content for a given chapter you need directly taught by me. You'll have access to me so that you can ask me direct questions. You can send questions, scan them, and I can, take a look at them. And I also have PDF notes that go along with those courses directly created by me. So hopefully, if you support the channel, if you'd like to take a look at that, I'll be having a video coming up very shortly that's going to make an announcement about that. So it's very exciting that we're starting to expand, because we're almost approaching 1,000 subscribers, and you guys have been great in terms of all the support you've shown me throughout the years. So thanks a lot, and I will see you guys for the continued lectures.